Hello, everyone. My name is Gabriel Almodovar. Today, I'll be presenting my research titled Joint Energy and Data Transfer Optimization in Collaborative Aerial and Ground Vehicular Networks. This work focuses on how unmanned aerial vehicles, or UAVs, can be integrated into a Space Air Ground Integrated Network, or SAGIN, to support autonomous land vehicles through real-time connectivity, energy-aware positioning, and efficient data transfer, particularly in areas where traditional infrastructure falls short. Now, a little bit of background of my experience. I am a Bobcat SDP student, SDP standing from Student Development Program. I am a controls engineer in the electrical team who designs and sustain electrical harnesses for our portable air compressors and generators. I am also an e-board member of the Society of Hispanic Professional Engineers, or SHIP. I am the professional development chair, and I am in charge of the professional affairs, including setting up networking events with companies, um, building resumes for many of our students, helping with elevator pitches and mock interviews. A bit more knowledge and background on the problem and the proposal that we're adding into our research is that our autonomous vehicles cannot navigate safely in real time when communication infrastructure is weak or is completely unavailable. Well, to solve this, I propose a SAGIN-based system where UAVs collaborate with land vehicles, optimizing their movement, energy use, and data transfer to fill those infrastructure gaps. Now, specifically, the objective for us from the semester has been to develop a mathematical modeling framework, one that accurately captures the behavior of UAVs and vehicles within a collaborative network. This framework sets stage for future simulations and optimizations. And a bit more information into the formulation method is that my process began with defining the core variables like UAV, vehicle position, vehicle velocity, whatever else it may be. I also ended up defining all these as a function of time across agents. What I mean by agents is that uh, the as I increase the network of UAV and vehicles, I will also increase the constraints as well as the functions to be able to work with an increased amount of UAVs or vehicles being simulated. Then I introduce a system of parameters such as mass, bandwidth, antenna gains, to be able to shape how the system behaves under real-world constraints. And finally, I constructed objective functions like minimizing latency or energy consumption that allow the system to be optimized mathematically. A little more information into the variable declaration of my formulation method. Each variable is expressed using tensor notation to handle multiple agents like UAVs and vehicles, all operating simultaneously. This structure makes the model scalable and adaptable for various network sizes. On top of that, I'm using a set theoretic notation to be able to further emphasize and have a better foundation when it comes to formulating in the future so that I don't have any gaps. Once I've done the variable declarations, I go forth with the function formulation. So I start assigning a function to every single variable that describes a certain parameter. Usually the functions are going to be of time, and these formulations are the most current part of my research, and they may significantly impact how the overall system is optimized. You know, they are the core of what you're optimizing. Once you have the functions developed and your variables declared, you can start parameterizing these variables. Um, I assign realistic values to the parameters based on typical UAV performance, um, vehicle communication hardware, or vehicle capabilities. These values will be used in simulations to evaluate the model's performance in real world scenarios. The most basic scenario we're using is one UAV and one vehicle traveling straight on a highway. But as we change the scenario, these constraints are going to change with it to be able to optimize for that given scenario. After that, the objective function, as I mentioned earlier, is a mathematical expression that defines what we're trying to optimize, whether it's minimizing energy consumption or maximizing data rate, or reducing latency. Will be the central in future simulations using optimization tools like MATLAB. Although you can also use many other more mathematical uh, approaches without having to use simulations, such as derivatives. Now, my my formulations are still uh under process. They are not done yet. And so as we're speaking, I'm still figuring out new ways to be able to improve my formulations as well as expanding upon them. Um, one of those things is an updated formulation strategy. So previously I had approached these the modeling individually for three main categories: UAV dynamics, land vehicle dynamics, and communication between them. It helped me to be able to correlate the relationships between all of them, but I ended up finding out a much better and elegant approach, which I'll mention in just a bit. The other issue that I had was that my model was complicating itself as I went. That was mainly because I was accounting for many different scenarios rather than concentrating in a simpler method. Now, this has an issue because if you have no simpler model to reference by, you just don't know how your more complex model can be, and it'll be very hard to interpret whether it's it's a good mathematical model, whether it's describing the correct things that you want without having a more simplistic approach. So you have to decrease the resolution of your model and then increase it over time as you learn more. Now, mentioning about the new approach models the UAV dynamics by optimizing the simpler equations that I mentioned earlier um, of land vehicle dynamics and also the communication model. This ensures that I am able to optimize these two variables and interpret the data that comes out of it to be able to develop my UAV dynamics much better. Once I'm done with my formulations, I will be able to put it through MATLAB, which is the software that I'll be using for my simulations. And I'll be able to start adding parameters and data into it to be able to actually test different scenarios. As I test the different scenarios, I'll be able to refine my mathematical models much better, as well as be able to see what happens as the data changes. One of the data samples that we have is the average velocity across different roads and areas in LA. And we'll be able to use this data to dynamically change the parameters uh, on our variables such that it can dynamically change the UAV positioning across, the highway while as the vehicle goes across the city or whatnot. Now, in conclusion, this research lays the foundation for a collaborative, intelligent transportation network that uses UAVs to fill the infrastructure gaps and supports autonomous vehicles in real time. By optimizing both energy usage and communication quality, we aim to improve the safety, efficiency, and scalability of autonomous mobility systems, particularly in areas where the infrastructure just isn't there yet. And with that being said, thank you so much for watching and enjoy the rest of the Scholar or your Scholar conference.